Hello everyone. Today we are going to talk about hypothesis testing, one of the most important tools in statistics. In simple terms, it's how we make decisions using data instead of just guessing or relying on opinions. Hypothesis testing gives us a structured way to test ideas and see if the evidence supports them. So let's start with this definition. Hypothesis testing is a fundamental statistical method used to make inferences about the population based on sample data. Think of it as asking, does the evidence from the sample support the assumption we made about the interpopulation? For example, suppose a company claims their newer battery lasts longer than the old ones. We can't test every battery, so we take a random selection of sample and use hypothesis testing to check if the claim is true. In the heart of hypothesis testing, there are always two competing statements. The first is the null hypothesis, often written as zero. It is like the default assumption. It says there is no effect and no difference. Relating it with the older example from the company one, we can say the newer battery has no difference than the older one. Likewise, the second is the alternative hypothesis, written as H1 or HA, which says there is an effect or difference. So we can we can again relate it with the previous example, like the newer battery are really more better than the old ones. So why is hypothesis testing significant? First, it helps us make informed decisions based on evidence instead of intuition. Second, scientists use it every day to validate or reject theories, which is how knowledge advances. And in industries too, hypothesis testing is crucial for quality control, making sure products meet standard before they reach customers. So it's not just a classroom concept, it's something used everywhere, from medicine to business to engineering. So now, hypothesis testing goes through five key major steps. Step 1, we formulate the hypothesis. We define the null and alternative hypothesis to be tested. After that, we set a significance level, usually 5%. This is how strict we want to be. After that, we collect data from a representative sample. Then, we calculate a test statistics, basically a number that measures how unusual the sample is under at zero. After that, we make a decision, either reject the null hypothesis if evidence is strong, or fail to reject if evidence isn't enough. Notice, it's not about proving something absolutely. It's about weighing evidence and making the best decision possible. So let's know more about the null and alternative hypothesis. The null hypothesis at zero is always a statement of no effect or no difference. For example, there is no difference in average test scores between two groups of students. Likewise, the alternative hypothesis H1 is what we want to prove. For example, there is a significant difference in test scores. Now, significance level and p-value. The significance level, written as alpha, is the threshold for rejecting the null hypothesis. The most common value is 0.05, meaning we accept a 5% chance of being wrong. The p-value is the probability of getting results at least as extreme as ours, assuming the null hypothesis is true. If the p-value is less than alpha, we reject the null value. We reject the null hypothesis. Think of it this way. If the evidence would be very rare under H0, then we doubt H0 and lean towards H1. Now let's talk about some situations. In some situations, we know the population variance. That's when you use the G-test. The formula compares the sample mean with the population mean adjusted for standard deviation sample size. In real life, this is less common, but it's an important foundation. Now for the unknown population variance, we often use the t-test. More often, we don't know the population variance. In that case, we estimate it using the sample variance and we use the t-test. The t-test is more flexible and works well with smaller samples. That's why it's used much more often in practice than the g-test. For hypothesis testing to be valid, a few assumptions need to hold. The data should be normally distributed, especially with small samples. Observations should be independent of each other. The samples should be randomly selected, and when comparing groups, the variances should be similar. If these assumptions are broken, the results can be misleading. Now, for comparing g-test and t-test, the g-test is used when variance is known and the sample is large, and the t-test is used when variance is unknown, which is almost the case. So in practice, most of the time we will be using the t-test. Now, some common errors in hypothesis testing. In hypothesis testing, a lot of mistakes can happen. So, type 1 error is a false positive. Rejecting a true null hypothesis is like convicting an innocent person. And another one is type 2 error or false negative. Falling, Failing to reject a false null hypothesis, that's like letting a guilty person go free. We try to minimize both, but there's always a trade-off. This decision matrix shows the four possible outcomes. Two are correct decisions, and two are errors. It helps us understand the risks involved and why choosing the right significance level is important. Hypothesis testing is powerful, but it's not perfect. With very small samples, tests may not be reliable. If we do too many tests at once, we increase the risk of false positives. Non-random samples can bias results, and one common mistake is misinterpreting p-values. A high p-value doesn't prove the null is true. It just means we don't have enough evidence against it. Also, we must remember, statistical significance doesn't always mean practical importance. So, to wrap up, hypothesis testing is about using evidence from samples to make decisions about populations. By setting up a null and alternative hypothesis, calculating statistics, and making a decision, we move from opinion to data-driven conclusion, whether in science, business, medicine, or engineering. Hypothesis testing helps us make informed choices, and that's why it's one of the most important tools in statistics.